Okay, so welcome to the lecture on chapter 3. In this chapter, we're going to introduce derivations and our first direct derivation rules, or rules of direct derivation. Now, this is going to be a really important video. It's a really central chapter because we're going to be doing a lot of derivations for the whole rest of the course. So make sure that you watch the video with close attention. You definitely want to do the practice for this one. You definitely want to stay on top of the problem sets for this one because it's going to give us a foundation for a whole bunch of the rest of the course. And this is true even if you have taken a different course, maybe another philosophy course or a computer science course or something, where you've learned how to do derivations, because our system, it might be slightly different. And you want to get the differences compared to what you've learned before ironed out. But of course, this is going to be explained, not assuming that you've learned anything before. But yeah, even if you have learned a different derivation system before or something, you should watch this, especially because it might be different with, for example, how we treat negations in our derivations. But anyway, forget all that. Let's just assume you don't know anything about derivations as we start talking about this chapter. All right. So let's remember valid arguments. So we'll remember that a valid argument is an argument which, if it has all true premises, must have a true conclusion, right? That's what we mean when we say an argument is valid. We mean that anytime all its premises are true, its conclusion has to be true as well. So how can we show that an argument is valid? Well, we can show that if its premises are true, its conclusion has to follow, right? So anytime all its premises are true, its conclusion will just have to be able to be shown, right? Because that will show that in any case where the premises actually are true, the conclusion will be true as well. And so we'll know that the argument is valid. So one way of doing this would be to take all the premises of an argument and using them, see if we can derive the conclusion, right? We want to think about, with all the premises we have in this argument, can we derive the conclusion? Can we show that the conclusion will be true, using the premises? And that's where we start thinking about doing derivations. We're going to try and take the premises and then derive the conclusion. Okay. So let's consider the following argument form. We know it's valid. Our premises will be if P, then Q, and then our other premise will be P, and then the conclusion will be Q, right? And we know this is valid. We know that if it's true that if P, then Q, and it's also true that P, well, then therefore Q will have to follow, right? And but note that we can also write this argument form like this. So in this case, we have our premises P and Q, or sorry, if P, then Q, and our premise P, right? All written out before the turnstile or the therefore symbol. And we notice that the premises are separated by this comma in between them, right, down here. So just at this point, you just need to know that this is a style of writing out argument forms that we're going to see a lot. You list the premises, you separate each premise with a comma, and then we have the turnstile here, which is like a therefore symbol. And it tells us the thing on the right of it will be the conclusion. Okay. So this is just setting up what we're going to do. But how can we formalize this argument's or any other argument structure to show that it's valid? Remember, we want to be able to have a system that lets us derive Q, the conclusion, from the premises, if P, then Q, and P, right? Those are our premises. We want a system that lets us derive the conclusion from it to show that the argument form is valid. So how can we do this? Well, we'll construct ourselves a derivation system. So we can make a system where, we treat the premises as true, and then we derive the conclusion, right? And this is going to end up looking a lot like math. It's going to look intimidating to those of you who are not familiar with that kind of thing, but just stick with it. It'll end up being okay. I'll walk you through how to build one, and then I will actually show you how we'll do it in our system. So I'll explain conceptually how you build one, and then I'll actually show you how we would do the derivation in Carnap. But anyway, yeah, we're going to construct a derivation system where we can show that, using premises, we can get the conclusion. To do this, and to explain our derivation system, we're going to start with a really basic argument, and then I'll explain how we use our derivation system to show it. So suppose I give you the following argument. It's going to be very simple. I say, my name is Ian, therefore my name is Ian. Well, the structure of this argument is just P, therefore P, right? That's all the structure is. We substitute in my name is Ian for P, and then we saw, well, the argument is of the form P, therefore P. And we write this out in our system as P with a turnstile P. Because what's on the left of the turnstile is the premise. So we have the premise here, and then we have the conclusion of the argument, the therefore statement, right? It's on the right side of the turnstile. It's P. Good. So now we can use a derivation system to show that this argument form is valid, right? Anytime its premises are true, which on this case is just the P on the left side, we can show the conclusion is true, which again is just P. So we'll produce a system that lets us show that anytime the premises are true, the conclusion is true, and therefore the argument is valid. Okay, so let's start our proof. So for all our proofs, we're going to use a big box like this. We're going to write all our derivations or our proofs in there. And you'll notice the first thing is that in this upper box, right here, we have the whole argument. We have where P is the premise, and we want to show P on the basis of our premise. So that's just tells you what the argument we're working with is. It's on the top there, right? And then we're going to start our derivation. Well, the very first thing that we want to write is, or that we want to put in our derivation is the conclusion. We want to tell the person reading our derivation or looking at our derivation, we want to tell them what it is we're trying to show, what the conclusion is. Well, in this case, the conclusion, as we can see from up here, is P. It's on the right side of the turnstile, right? So we write show, we put a colon here, and then we put a space and we put P, because we're just writing down what we're trying to show. And you have to write it out this way. You have to write show, you have to put in the colon, a space, and then P, or whatever the conclusion is. The system will give you this number automatically. The numbers just tell you what line you're looking at in the derivation system. Okay, but yeah, so the first thing you always do is you write the conclusion of the argument you're considering, and you call it your show line. You put show, colon, and then whatever it is you're trying to prove. Okay. Now we want to add our premise to the proof, right? Because we want to show that we can derive the conclusion on the basis of the premise. So we'll have to include that in the proof somehow, right? So after we write our show line, you hit enter on your keyboard, or if you're doing this on pencil and paper, you just start a new line, but you hit enter on your keyboard. It will produce a line number 2. But then before you start anything else, you have to hit space. Space bar will produce this line here, which is an indent. And the indent tells you that you're working towards what you're indenting under. So you're working towards showing what's on the conclusion, or the show line, right? You're working towards showing the conclusion. So you indent under the show line, you hit spacebar, you get this little line, right? Now we're trying to use our premises to show the conclusion, right? So we list our premises then. In this case, we only have one premise. It's P, right? P is our premise. It's on the left side of the turnstile. So we just write P here after we do our indent, and then we put a colon, and then on the right side, we have to tell the reader of this derivation where we got this line in our derivation, where we got line 2. Well, we got line 2 just because it's a premise of the argument, right? So we just write PR. That tells us it's a premise in the argument. That's how we got it. So we have P there. Great. Yeah, so that's how you list your premises. Sometimes there'll be a lot more premises than just one. You'll know because there's a comma separating them, as we saw before. But yeah, so first you write your show line just like this. Then you do another line where you indent, and then you list your premise. And then you make another line, however many premises you have, you make another line, you write that premise, you call it your premise, you're good. You'll see in the examples we do, but we're starting with something pretty basic. Okay. Now you'll see already, right? We wanted to show P. That's what we wrote at the beginning, right? Well, in our premise, we have P. This is such a basic argument that the premise just has the conclusion in it. So look at that. We treat the premise as true. We have it here. We put it in our derivation. We wanted to show P. Well, we already found it, right? It's just the premise, right? So we've done it. We've shown that if the premises are true, you can get the conclusion. Well, because in this case, the premise is the same as the conclusion. So we already have it. So ta-da, we did it. We found the conclusion we wanted. We found what we were looking for on the show line. And so in this case, we can just close the derivation. We can say we did it, we're done, we're closing the derivation. And so in this case, you hit enter, you start a new line, and we're writing our conclusion line. Now we don't need to indent this time. We don't need to hit space because we're closing the derivation. We're not working towards, finding the conclusion. We already got it. So in this case, we just end up write a colon. We put DD for direct derivation. And then we say where we got the conclusion we were trying to show. Well, we got it on line 2, right? So you can see again what we did was we wanted to consider this argument, right? P, therefore P. To do this, we used a derivation. So the first thing we did was we wrote the conclusion we were trying to show, which was P. Then we listed our premise, which in this case was also P, which is very nice. And then we noticed, as we're looking at our derivation, we already have what we're trying to show. So we can just close the derivation. We said that we used a direct derivation, which is what we did. It appears directly there in the proof. There's a line with it right there. And we said what line that we got the thing we were trying to show on. We got it on line 2, so we write 2 there. And that's great. The proof is closed. We showed that the argument form is valid. We showed that if you have the premise P, you can get the conclusion P. That's great. We did our derivation. Excellent. Okay, so now I'm going to show you how this looks in our Carnap system, just so you can see it again and you can see me type it in. This is also, by the way, the first question in the problem set for this chapter, so you'll want to pay attention to how I do it. Okay. So let me show you how to do this in Carnap. Okay, so here we are in the Carnap textbook with the problem sets. It's in chapter 3. You can just get to the problem sets how you normally would. As always, make sure you're looking carefully through the textbook because it's possible there's a problem set in the middle somewhere. You don't want to miss one. But for this chapter, for chapter 3, we only have problem set 4 and it's at the bottom of the chapter, so that's great. Okay, so I'll zoom in a bit here and go back to the problem set. Okay, so you can see that what we're looking at is the same argument we just considered. So let's look again at how we write it out in our derivation system. Well, if we're going to do a derivation for this argument, the first thing we have to do is write the conclusion, right? We want to say what we're trying to show. In this case, since it's on the right side of the turnstile of the therefore symbol, we just write that we want to show P. We write show, we enter a column, and we put P. And that's great. Then you hit enter to make a new line. Now we're working towards showing this, right? So the first thing we have to do is indent. So we hit spacebar, and that produces a black bar there, as you can see. And now we want to list our premises. That's always the first thing we do when we do a derivation, is we list whatever premises we have. Well, in this case, we have the premise P, so we hit P, we just write P, hit spacebar, and then we need to say how we got this P, how we got this line in our proof, right? Well, we got it because it's a premise. So we write a colon, we write PR to say it's a premise, and our line is good. So let's start another line. Okay. Now remember, we want to show P, right? Well, conveniently for this argument, we already have P, it's a premise. So we can just close the proof. We wanted to show P, we got P. So in this case, we're closing the proof. We don't need to indent because we're saying we're closing the proof. So we just immediately write a colon. How did we get the proof? Well, we did a direct derivation, so DD. And where did we get, so we wanted to show P, we got P. What line did we get P on? Well, we got it on line 2. And look at that. It's ready. It's done. We got a green check mark. We know the derivation is complete and good. So that's excellent. These arrows over here will tell you whether things are done or if they're working well or whatever. So for example, if I didn't close this yet, the show line would still be open because it was never closed, right? But once we write our close line, everything is happy and it's good. Anyway, yeah, so these will just tell you different errors that you have. Yeah, okay. So we close the proof, it's great. For your problem sets, you're gonna wanna hit submit once you have a correct proof. If I do it, it says I've already submitted this because, I've done it before. But for yours, it'll say successfully submitted or whatever. Yeah, okay. So that's how we do our first proofs. So there you go, that's the example. Let's go back to the lecture. All right. So this derivation shows then that all arguments of the form P, therefore P, will be valid, no matter what P is, no matter what you substituted in. If you have the premise P and you have some conclusion P, then it's always going to be valid. So, what this is going to indicate to us is that whenever we're doing derivations, we're almost always not going to be concerned with a normal English language argument. Like I gave you an example of the argument, my name is Ian, therefore my name is Ian. But this was just to explain the concept. When we're doing derivations, generally, we're not concerned with actual English language arguments. We just want to know about argument forms generally, right? And so we'll be working generally with P or Q or R, or claims like if P then Q, or claims like P and Q or whatever. And you could substitute in any sentence for those letters. Yeah, and this just lets us use derivations to consider whether a given argument form is valid, regardless of any particular English argument we substitute in. Now, in the last lesson of this class, I explain a little bit how all of this can be used with real arguments, but we're not going to really be focusing on that in this course. But if you're curious, you'll be able to see that. It's the last lesson of the course. Okay, so we have just been able to prove something where the conclusion is just given in the premises, right? We wanted to show P and we already had P in the premise. So that's great. But sometimes we need to generate new lines to show our conclusion. So for example, we can go back to this argument that we were considering earlier, right? We have this argument form here that we looked at a bit earlier, where the premises are if P then Q and P. And the conclusion that we want to show is just Q on its own. So you'll notice in this case, in the premises, we don't have just Q on its own, and we want to show just Q on its own. So we can't just say, oh, it's in the premise, like we did with our previous argument, because, when we make all the lines, we won't find that Q on its own is just in a line when we list our premises. So rather, we're going to need a way of producing Q on its own from the premises that doesn't just refer to a premise. For this, we need to be able to generate new lines, right, in our derivation. And so we're going to need rules of direct derivation that give us rules for how we can produce new lines. So the ones we're going to start with, we're going to call them MP for modus ponens, MT for modus tollens, DNE for double negation elimination, and DNI for double negation introduction. And this sounds like a lot, but you'll see how it works. So let's start with modus ponens. So modus ponens, which we're going to call MP, is a rule like so. So if you have two lines of the form P and if P then Q, then you can get Q on a new line by using the rule MP. So how this will look in our system, I mean, normally these will be indented or right, because you'll be showing an argument, but this is just how you get it without thinking about the indents. I'll show you how we use it with indents in a moment. But, suppose on one line you have P, suppose on another line you have P arrow Q. In this case, we'll call them premises, but they could be anything as long as you have them on a line. Yeah, so if you have a line with P, you have a line with if P then Q, then you can just output Q by using modus ponens. So, after the colon, it always tells us how we got this line. Well, in this case, line 3 was gotten by using modus ponens, MP. And how was it used? Well, we used it on line 1 and line 2, because on line 1 we had P, and on line 2 we had if P then Q. And so when we use modus ponens on those two lines, well, then we can get this new line with Q, right? Yeah, and now you should also note that anything could substitute in for P or Q in these scenarios, right? So for example, if you have Q and you have if Q then S, then you can get S by using modus ponens. See how it looks basically the same. All we did was substitute in different letters in for P and Q. But also, you could even do it with more complicated lines, as long as the main connective of the line with the arrow, the if-then claim, as long as the main connective is if-then, and you have another line that has whatever's on the left of the if-then. So in our simple examples, we have if P then Q, right? Where the main connective is this if-then, and we have a line with the left side of the arrow up here. We have just a line with P. And so we can get the right side, right? We can get Q. So you can do this with more complicated sentences as well. So if you have, for example, this more complicated claim, you have if P then Q, then R, right? And on one line you had if P then Q, then you could just get R. So look down here, right? So on line 1 we have if P then Q, then R. And on line 2, we have if P then Q, which is the left side of the main connective arrow, right? So we have the left side of the main connective arrow on line 2. We have the left side on line 2, and we have the main connective arrow claim on line 1. So we can just get the right side of the main connective claim, right? By using modus ponens on lines 1 and 2. So again, this all sounds, I'm sure if you've never done this before, it sounds a bit weird. But let me just show you really quickly how this looks in our system, and then we will come back to our other rules. Okay, so I don't want to give you all the answers to all the problem set questions, right? So instead, I'm going to show you how all this works on our practice documents. So in this case, we have this chapter 3 and 4 practice in our chapter 3 module. Maybe this will look a little bit different for you, but something like this anyway. You'll on Brightspace. So you just click the practice document. It'll bring you here. Obviously, we're just looking at chapter 3 right now. So let's use modus ponens here. So let's look again at our argument we're considering. Well, we always want to write that we're trying to show the conclusion, right? That's how we start. In this case, the conclusion is Q because it's on the right side of the turnstile. So that's great. Now we want to list our premises, and you'll notice in this case we have 2 premises, right? So we just want to list all of them. So first we have if P then Q. I'm just going to copy paste. Oh, you should always indent, remember. Always indent at the beginning of your line when you're working towards a derivation. So you hit space, you indent, and then you write the premise, and you tell us it's a premise. That's how you got it. And then we also have this other premise here, P. So we put that in after we indent, and we've listed our premises. Well, we need a line with just Q on its own, right? So how are we going to do that? Well, we're going to use our new rule, modus ponens. So we start a new line, we indent, and we know we can get Q by using our rule modus ponens, right? Because to use modus ponens, you have a line where the main connective is a if-then, it's an arrow, and you have another line where you have the left side of the arrow. So in this case, we have P, it's right here. It's the left side of this arrow claim. So we know we can get Q. We know we can get the right side of the arrow. So we have Q. And how did we get it? Well, we used our new rule, modus ponens, right? And what lines did we use? Did we combine to get this? Well, we combined lines 2 and 3. So we write that out. And look at that, everything is good, it's going well. And in fact, remember, we were trying to show Q. That's what we wrote at the very beginning. So we just Notice that we've already got it on a line, and we can close the proof just like we did before. When we're closing the proof, we don't need to indent, right? So we just write direct derivation, and we write that we did it all on line 4. There you go. Derivation is done. We used our new rule, modus ponens. Okay, back to the lecture. Okay, so that was modus ponens. Now we're going to do modus tollens. And it's pretty similar, but kind of reverse. So here, I'll give you an English language example so you can understand it better. Now, suppose I say to you, if I go to the store, I will buy milk, right? Suppose I say that to you. And then we also find out that I didn't buy milk. I did not buy milk. Well, then we know I didn't go to the store, right? Because I said if I went to the store, I would buy milk. The fact that I didn't buy milk thus shows that I didn't go to the store. Because anytime I went to the store, I would have bought milk. So that's the kind of reasoning process that we'll use here, right? So modus tollens, or MT as we'll call it. So if you have two lines of the form not Q and another line of the form, or if you have a line of the form not Q and you have another line of the form if P then Q, then you can get not P on a new line by using our new rule MT, modus tollens. So you see here on one line we have not Q, on another line we have if P then Q, and so using our rule MT, right, we can get this line not P. Great. Yeah, so you can see how this is kind of the opposite direction of modus ponens. Whereas with modus ponens, if we had the left side, we could get the right side. In this case, if we have the negation of the right side, we can get the negation of the left side. So it's kind of like going backwards and reversing it. And I'll show you an example in a moment. But note again that the same rules can apply. We can substitute anything in here for P and Q. What's important is that if we have an if-then statement, so for example, we have if R, then P, then Q, right? And if we have the negation of the right side of the arrow, right? So on line 1, we have the negation of if P, then Q. And on line 2, the right side of the main connective is if P, then Q. So if we have the negation of the right side of an if-then claim, then we can get the negation of the left side, right? And it doesn't matter what you substitute in. So here we have like a more complex example, but it works the exact same as this more simple example up here. Okay. So let me now show you how this rule works in our derivation system. Okay, so this is the same practice document I just used for my other example, but let's walk through using modus tollens. So we always, again, we write the conclusion, show not P. Remember, that's what we're trying to show. And then first thing we do always is we list our premises, right? So in this case, it's P arrow Q. It's a premise. In this case, not Q is a premise. So that's great. And we remembered to indent these two lines because they're helping us work towards this conclusion. But we want to get not P. So we start a new line, we indent, and then we look at what we have here. Well, we have an if-then claim on this line here, and we have the negation of the right side of that claim, right? So that means we can get the negation of the left side. So we can get not P using modus tollens, MT, on lines 2 and 3. Look at that. Excellent. And now we got not P, we were trying to show not P, so we can close our proof. We did a direct derivation, it's closed, it's ready, and we got the conclusion on line 4. There you go. Excellent. Okay, so now we are going to talk about our double negation rules. So the first one we're going to talk about is double negation introduction. We're going to call this DNI, right? Now this one is easy enough to understand. All it means is that you can add two negations to any line you have. You can add a double negation, right? You can introduce a double negation to any line you have. And this makes sense in some way, right? Because if I say my name is not Ian, that's kind of like saying my name is Ian. So if we know my name is Ian, then it seems fine for me to introduce a double negation onto it and say my name is not Ian, right? So that's the kind of idea. Yeah, so the rule just lets you add two negations to whatever. So you can say using DNI, double negation introduction, you can add two negation symbols to the left of any line you already have in your derivation. That is, you can introduce a double negative. So if you have a line with P, you can just make a new line with not P by using DNI. So you see here we have a line with P. Well, we can just get a new line, not P. We write DNI. That's the rule we use to get this line. And we write which line we added a double negation to. In this case, we added a double negation to line 1. And again, the same substitution rules apply. You can substitute anything in for P. It could be like R, and then you add a double negation to R. Or it could even be the whole claim, if P then R, and then you add a double negation to the whole claim, if P then R. Just make sure you don't, in this case, add a double negation to just P. No, it has to be to the whole claim, right? You have to put the whole claim in brackets and then add a double negation. So let's see how this works in our system. So here's an example where we want to show not P, right? So we write that out. And then in this case, we have a premise that's P. So we indent and we write our premise. First we write the show line, what we're trying to show, which is just the conclusion, and we list our premises. In this case, we only have one premise. Great. And then how can we get this? How can we get not P from P? Well, we can add a double negation to it, right? We can do not P. And how did we get it? Well, we used our double negation introduction rule, right? We introduced a double negation. And we can use it, or what did we add the double negation to? Well, we added it to what we have on line 2. So we write line 2. And there you go, you got what you wanted to show. So again, you close the proof. You did a direct derivation, you got the conclusion on line 3. So there you go. All right, and our final rule that we'll be adding is very similar. This one is double negation elimination, right, or DNE. Now, this is the same thing, except we just eliminate two negations, right? So anytime we have a double negated line somewhere, we can remove two negation symbols. And that is, you can eliminate, this should read eliminate a double negative. So if you have a line with not P, for example, you can derive a new line P by using DNE. So you see in this example, we have a line not P, and then we get a new line just P by removing the two negations. So we did a double negation elimination. And we said what line we did that to. Well, line 1 had the double negation that we removed to get this new line. So we say we did it to line 1. And as always, the same substitution rules apply. Both of these examples below here are perfectly good ways of using DNE to get a new line. In this case, we do it to R. And in this case, we do it to a more complicated phrase, right? We have this double negated if Q then not P. Well, we can use double negation elimination to just get if Q then not P without the double negation. Okay, so let's again do this in our Carnap system. Okay, so for this one, we're gonna do a double negation elimination. And just to show you, like, you really can substitute in different things for it, I made this one a little bit more interesting, but only a little bit. Okay, so as always, we want to write what we're trying to show. It's always whatever's on the right of the turnstile. So in this case, we want to show not Q, right? And then we list our premise. Well, in this case, we have not Q. That's our premise. And we need to indent it, so don't let me forget. Okay. Well, we want to get not Q, and we see this one has not Q. Well, double negation elimination lets us remove two negation symbols, correct? And look, we have 3 here. So, if we get rid of 2 of them, we're going to just have not Q. and not Q is exactly what we're trying to show. Remember, double negation elimination lets us remove specifically two negation symbols from any line we already have. So in this case, removing two of these will just leave us with not Q. So on our new line, we can get not Q. And how did we do it? Well, we did double negation elimination. And what did we eliminate a double negation from? What did we eliminate two negations from? Well, we eliminated it from line 2. Right? So look at this. We have on line 3 not Q. We were trying to show not Q. So everything is great. It's good. So we can just close the proof on line 3. There you go. So that's double negation elimination. You can always eliminate two negations from anything, and you're good to go. All right, so those are our negation rules. I see my video is cutting off the text there a little bit, but this is just a note for those of you who have maybe learned logic in a different class. If you've never learned logic before, ignore this because this won't be a problem for you. But if you've learned a derivation system in a different class, please pay attention to this. In our system, we can't treat a claim P and its double negation not P as the same, okay? If you need P and you have not P, you have to do a double negation elimination to get P. You can't just treat not P as P. I know in some logic systems, some derivation systems, you can treat them as identical, but in our system, no, you have to do the double negation, right, to make sure that they're the same. You can't use them as if they're the same. So for example, if you want to show P, you can't just, okay, sorry. For this example here, you'll notice we want to show P. You'll note that you have not Q, and you want to use if Q then P to get P using modus ponens. Well, you can't just, treat line 2 as Q. It's a not Q. So rather, you would have to do what we do over here, where before doing the modus ponens, you turn the not Q into a Q. Okay, great. So that's just a note for those of you who learned derivations in a different class. But for those of you who had never seen that, just ignore it. Yeah. All right. So now we've talked about how to use these rules. We've talked about rules of direct derivation. But sometimes you're going to need to combine them, and so I'll just do some practice examples now where we use the rules kind of in more combined ways, right? All right, so let me show you how to do that. Okay, so let's do some practice. Hopefully you've written down all the rules, so you just have them in front of you. That would be handy. What we're going to do is just look at some of the practice problems from the practice document on Brightspace. I'll go down to the combined rules section. Okay, so let's start with this example here. So the first thing we always want to do when we do any derivations is we list the conclusion, or we write what we're trying to show. In this case, it's Q. And then we list all our premises. So in this case, we have the premise P. We indent, we write the premise. And we have this big long premise here. So we'll make a new line where we list that as our premise. Now, what can we do here to try and get Q? And let's consider the rules we have. Well, our first rule was modus ponens, where if we have what's on the left side of the main connective arrow in a claim, right? So in this case, this is the main connective arrow. If we have what's on the left side, then we can get aligned with what's on the right side. Yeah? So let's do that. Well, you see we have P, so we have the left side of this main connective arrow. So we can get the right side, which is all of if P then Q. And we did that by using our modus ponens rule, our MP rule. And we used it using lines 2 and 3. Right? So that's great. Well, we still want to get Q. And we have this new line here, if P then Q. Well, again, we have what's on the left side of this main connective arrow. We have P, right? It's up here on line 2. So we can do it again. We can do another modus ponens. We have the left side of this arrow, so we can get the right side. So we get Q, we did modus ponens, and we did it using lines 2 right? And in this case, line 4, right? Because we're combining line 2 and line 4. And there we go. We wanted to show Q. We got Q, so we can close our proof. We did a direct derivation, and we did it on line 5. That's where we got the conclusion. Okay. Good. Great. Here, let's do this one. So in this case, we want to show Q, right? This one will have us combine some of our rules. So we always write that out. And then we write out our premises. In this case, we have, we write an indent, we put in not P, that's one of our premises, and we do an indent, and in this case, we have if not Q, then P. I deleted the brackets just because I think it looks better, but you can leave them on if you like them. Anyway, so in this case, we're trying to get Q, and we have these premises. So how are we going to do it? Well, let's look at what we can do just with our premises. In this case, we have a not P, and we have a if not Q, then P. Well, let's think about our rule modus tollens, right? MT. We know that if we have the negation of the right side of an arrow, then we can negate the left side, right? So we have the negation of the right side of this arrow, right? On line 2, we have not P, and the right side of the arrow on line 3 is just P. So we have a line where we have the negation of the right side. So that means we can get the negation of the left side, right? So we can add another negation to what's on the left side of this arrow. So we can get not Q. And how do we do that? Well, we did modus tollens, remember, MT. If we have the negation of the right side, we can get the negation of the left side. And we did that with lines 2 and lines 3. Okay. Well, we want to get Q, right? That's really what we're trying to get. Well, on this nice line that we have here, this nice new line, and again, we'll always indent our new lines. On this line here, on line 4, we have not Q. Well, let's think about what rules we have and what we can do to maybe get Q. Well, we have this nice double negation elimination rule, right? It lets us eliminate a double negation. So in this case, we can take our not Q and we can just get Q. We eliminate this double negation. So how did we do that? Well, we did a double negation elimination and we did it to line 4. So we write that out. And look at that, we have Q, which is exactly what we were trying to show. So we can just close our proof. We got the conclusion on line 5. And everything is good. Everything is fantastic. It's complete. It's good. Okay. So let's do one more over here. Has another combination of rules, right? So let's do, like we always do, let's write that we're trying to show the conclusion. In this case, it's Q. And let's list our premises. So we have P as a premise. And we have if not Q, then not R as a premise. Great. Okay. So how are we going to get Q? Well, we can see we have a not Q over here. So we can think to ourselves, well, gee, if we can get a negation on that, we'll have a not Q, right? And if we have a not Q, then we can just get Q by double negation elimination. So that would be nice. So how can we do that? Well, we know that if we can have the negation of this, right, of the right side of this if-then claim, then we can add a negation to the left side. And then we could just do a double negation elimination. Well, how can we get the negation of this side? Well, conveniently here on line 2, we have P, and we know that we can add 2 negations to any line we already have, right? So let's do that. So let's take this P, and we'll write not P, right? We can get a double negation introduction. We introduced a double negation onto this line, onto line 2. Well, look at this. Not P is the negation of not P. That's great, right? That means we can use modus tollens, because we have the negation of the right side, to get the negation of the left side. And look here, we have the negation, we have not P, which is the negation of not P. So we can get not Q, which is the negation of not Q. right? So we get not Q. And how did we do it? Well, we used modus tollens using what we have on line 4 and line 3. Right? Now look, we have not Q. And if we remember, what we're really trying to show ultimately is just Q. Well, luckily we have this double negation elimination rule that lets us get rid of both of these negation symbols, right? So we can get a new line where we have Q, and we write double negation elimination, line 5. So that's great. We finally got the conclusion we wanted. So we can close the proof. We did a direct derivation, and we got the conclusion on line 6. So there you go. That's how you do it. So, there's a lot of practice in this. Go through it step by step. Each section tells you what you're supposed to, what rules you should look for. So this first group of questions wants you to use modus ponens. So that's great. This section, next section wants you to use modus tollens. So that's great. And then there's these double negation rules. So double negation introduction and elimination. And then finally, there's this section where you just use whatever rules seem to make sense in the situation. Okay. Okay, so that's all the introduction to direct derivations, to derivations in general. Please, do your best on these. Do the work as soon as you watch the lecture, because you want to be able to ask questions in tutorial and in my question section, and you don't want to wait to do your work until after those sessions have already happened, because then you won't be able to ask your questions. Yeah, so just a note on what might be helpful for you. There is in the Brightspace a reference guide for listing all of the derivation rules that we have. You only need the first 4 of them, the ones that we learned in this class. You only need MP, MT, double negation elimination, DNE, and a double negation introduction, DNI. You only need those 4 for now. So if you go to the file on Brightspace that has the reference guide, there's going to be a lot more stuff there. You don't need to worry about it just yet, but it will help you be able to know when and how you can use those rules. All right. So yeah, so that's the conclusion to the lecture. That's chapter 3. Do the problem sets, do the practice, ask questions. It might look very intimidating to you now if you've never done any logic stuff before, logic derivations, but I promise practice, ask questions, and it'll be doable. Okay. Great. So thank you, and see you in the next lesson.